Good morning, everyone. Let me double check. Is this on? Yes. Recording's on. We're ready to start. So good morning. I hope you're all doing well. Let's continue. Today we're hoping to finish sets 3 and 4 so that you can do them over the weekend. Okay, so this is where we were at last time. Any questions before we start about anything? Okay. So remember, we were talking about the general continuum that deforms and rotates and moves. And we said that we're going to start with a very simplified, from continuum we went to a rigid body and then we went to a particle. We're going to start with a particle and then we're going to recover the rigid body later on in the course. So for a particle moving in 3D space, we define its position vector r, its velocity vector v, which is the rate of change of the position vector r with respect to time, and a, the acceleration vector. We also define the arc length coordinate s by this relationship, ds by dt is dr by dt. And then the direction of the velocity of the particle is always tangent to its trajectory. We define that unit tangent direction to be et. So remember, we have v is dr by dt, and I can apply the chain rule under certain conditions. Dr by ds, ds by dt, where this vector is a unit vector, which we call the et. So that's the speed, that's et. So that's and if we take the derivative of this, we will get the acceleration. So the acceleration is equal to what? Right, which is what's the derivative of this? We're going to need to use what? The product, exactly. So that's going to be v dot et plus v et dot. And we said that the acceleration of the particle is the rate of change of the velocity vector. So the velocity is a vector. It has magnitude and direction. So its rate of change is going to depend on both. This part depends on the rate of change of the magnitude of the velocity, which is the rate of change of the speed. And this part has to do with the rate of change of the direction of the velocity. Any questions? Does that make sense? Questions? Okay. So what I want to do right now is I want to look at the very special case of a particle moving on a straight line. That's called rectilinear motion. Okay, so we're going to take a particle to be moving along a straight line, and I'm going to take the unit vector ex to be along that line. So in general, I can express the position vector of the particle r in terms of x ex plus y ey plus z ez, right? But if the particle is moving along a straight line, and I'm taking ex to be parallel to that line, so now my particle is not moving on a random curve. It's moving along a straight line that is parallel to x because that's how I chose ex. What is special about these y and z components here of the position vector r? Yes? They're zero. They're constant, right? The rate of change is 0. So these coordinates are not going to change as the particle moves. So as the particle moves, the x coordinate of this vector is going to change. Wait, I do this kind of messed up. Ex, ey, ez. Okay, so as this particle moves, the x coordinate of this vector is going to change, but the y and z coordinates are not. So when I take the derivative, I just have x dot ex. Okay? So y dot is equal to 0 and z dot is equal to 0. Similarly, the acceleration is going to be x double dot ex. Question. Are s and x the same here? So s, what is s? It's the arc length coordinate, right? I can be more specific, or so that I remove the dependence on initial conditions, I'll just put our s dot and x dot the same here. Take a minute, think about it. You can chat with your neighbors, and then I'll take your input here. Raise your hand if you think the answer is yes. Raise your hand if you think the answer is no. The answer is no. Think about it. No meaning not always. There's a special case or some condition for under which s dot and x dot are equal. Think about it. Think about it. Let me know what you think. Any opinions, any ideas? Yes. Exactly, exactly. So if the particle has velocity v like this, I know that v is vet, right, from over here, or ds by dt et, which is equal to, from here, x dot ex. So basically, it's s dot et plus x dot ex. So then, if the velocity is this way, what do we know about et and ex? They're the same, right? However, okay, so if et and ex are the same, then s dot and x dot are equal. But if the particle is moving like this, then et is equal to what? Negative ex, then s dot will be minus x dot, right? So s dot and x dot are the same if et is equal to ex. Always, you're moving along ex. So this is because of our convention for how we defined s. So there are other definitions of s where s is not defined depending on how the particle moves on the curve. It's just defined according to a positive direction along the curve. So they kind of say that s is always positive as I go like this, s increasing. So they define s along the curve and not related to how the particle moves along the curve. Whereas this definition here, it takes into account the motion of the particle around the curve. So just a clarification here. So then in my case, in this definition, s dot is always, is it always positive? Yeah. But any questions? Questions? Okay. So if et is always equal to ex, s dot and x dot are the same here. Okay. So let's assume that's the case. So I have that v is S-Ex, S.Ex, or V-Ex. And A is double dot Ex, which is V dot Ex, which I will call as AEX. So now I'm going to use the chain rule again for rectilinear motion. So what I have is that A is equal to dV by dt, which I will write as dV by ds by dt. Now A is AEX, dV by ds, I will call that dV by ds Ex times ds by dt, which is, what is ds by dt? I already called it V, right? This B. Okay, so I took this equation here. No, actually. I took the equation A is equal to dV by dt. The acceleration is the derivative of the velocity with respect to time. And I introduced the chain rule, dV by ds, ds by dt. dV by ds is just dV by ds along Ex, where V is Vex. And ds by dt is V. So I can project this equation along Ex. Now, what does that mean? So this is kind of simple here because all of the components of this equation are along Ex. I can basically cancel out the Ex, and I'll get that A is equal to V dV by ds, a scalar equation. So I can go from a vector equation to a scalar equation. But really, mathematically, what's happening behind this cancellation is that I'm projecting this equation along Ex. What does that mean? I'm taking the dot product of this equation, of every term of this equation with Ex. So this means so I go from a vector equation to a scalar equation. Okay, so this is how I do it. I have this vector equation. AEX is equal to dV by ds times VEX. And I can, this is how I usually denote it, dot Ex. That means I'm taking the dot product of every term of this equation with Ex. What is Ex dot Ex? 1, right? So this is 1, this is 1. I'll get A is equal to dV by ds times V. So this projection is very, very simple. But why do I focus on this? Because later on we're going to project equations where different vectors of the equations are not even expressed in the same basis. We're going to introduce new bases, the cylindrical polar bases, the serif-René bases, other correlational bases. So we're going to have long equations where the vectors in these equations are expressed along different bases. So to project, this is what you're doing. If you're projecting along a certain direction, you're taking the dot product of every term of this equation along a unit vector in that direction. So here I get A is equal to dV by ds, A dV by ds times V. Maybe you've seen this before as A ds is equal to V dV. So what is this equation? Well, any questions? We will practice projections and we will practice problems with rectilinear motions. Yes?
Wait, why are you projecting if it's already AEX, if it's in terms of EX?
Because I want to get the scalar equation out of the vector equation. I want to get rid of this EX. Yes. This is a very simple case. You probably can say that projection here is not necessary at all. but we're going to do more complicated cases. So I'm explaining the method. Yes?
This is more of a hypothetical, but do you need to use a fixed basis to dot?
Do I need to use what?
Like a fixed basis, like.
Oh no, you can, that's a great question. You can dot with any unit vector. Yeah, you can take the dot product with any unit vector. A projection along any direction, which could be moving, which we're gonna do, and it's gonna be convenient in some situations. Yeah. Any other questions? Okay. So let us go back and see where we can apply this equation. So this is basically a relationship between acceleration, speed and arc length or position of a particle moving in rectilinear motion that's independent of time. So you can imagine a situation where, like, I'm driving a car and the car is decelerating. I'm given the speed of the car before it decelerates, the acceleration of the car or the deceleration of the car, and you want to find the speed or the distance traveled by the car until it stops. So then you have the speed, you have the acceleration, you want to find the distance. You're relating A, V, and S without explicitly depending on time. So I'm not asking for the time I need to stop. I'm asking for the distance I need to stop. So in a situation like this, this equation will be useful. Let us see. Okay. So I'm going to just maintain the order from the notes here. Okay, so say we are given the acceleration as a function of speed. And we're going to do an example in a bit which involves that. So I have acceleration as a function of speed. Then if I go back to this equation and I plug in A of V ds is equal to V dV. Remember that V is equal to S dot. A is equal to V dot, which is S double dot. What kind of equation is this? Does it have a name? Yes. Exactly, it's a differential equation, right? Because it relates a variable and its derivative. So that's a differential equation. Okay, so if you're solving an algebraic equation x is equal to 2x plus 4, you solve for the variable x. If you're solving a differential equation, for example, A of V dx is equal to V dV, what are you solving for exactly? What's the solution going to be for a differential equation? Is it going to be a variable equal to a number? No, it's going to be what? A function, right? I'm going to get a function. So here I'll get S as a function, or for example, V as a function of S as a function of T. So I'm solving for a function. So here I'm solving for the motion of the particle, right? Can I solve this differential equation by hand? It is a special kind of differential equation that's actually quite easy to solve once we know A of v, but have you taken a differential equations class? Yeah, a little bit. You would learn this at the beginning of your class because you can actually solve this by taking a regular integral. This is called and you guess it.
Separable.
Exactly, it's a separable differential equation. What does that mean? I can separate all the v variables to one side. I'll get v over A of v dv ds. And then I can separate all the s variables, all the functions of s to one side, all the functions of v to the other side, and now I can integrate. Okay? And I can solve for s as a function of v. If I integrate, I need to put initial conditions, so that's going from v at t equals to 0 to v of t at t equals to t. And I want to differentiate between the speed at the boundary and the speed inside the integral, which is just a dummy variable. So I'll put it tilde. Same thing here. I'll put it tilde s t equals to 0 s at t. Because I want to differentiate again between this s, which is a dummy variable, can have any name, and the s that's on the boundary of the integral. So you can imagine if I'm giving a particular a of v, for example, a of v is equal to v squared or 1 over v or whatever, I can integrate and I can solve for s in terms of v. Do we get this almost? We're going to do an example, and then if you have any questions, let me know, okay? Any questions in the meantime, though, about these calculations? Okay. So I think the second case is given acceleration as a function of displacement. Ooh, I keep forgetting. It's not working. Okay, so acceleration now is given in terms of s. If I plug that into my relationship here, a ds is equal to v dv, I'll get. Okay, what do we notice about this equation? Yes. Exactly, they're already separated the variables, so I can just integrate. And I don't have to integrate from t0, I can integrate from any time to any time. So this is already a separable differential equation. Okay. If I'm given acceleration as a function of time, then usually this relationship is not useful to me anymore. I'll use the a is equal to dv by dt, which says that a of t is equal to, or a of t dt is equal to dv, and now I can integrate. So I skipped a step here because I don't have space. Any questions? Okay. We'll do an example in the context of rigid body kinetics, which we're starting now. Sorry, particle kinetics. Any questions? So a particle has a mass. We also define a quantity for a particle, which we're going to call the linear momentum. The linear momentum of a particle is its mass times its velocity. So that's a vector, right? So the linear momentum of a particle we're going to give it a symbol G. So G is equal to mv is by definition the linear momentum of a particle. So if I have my phone to be a particle, if it's moving at a higher velocity, the magnitude of its linear momentum is going to be higher. If its mass, if it's heavier, the magnitude of its linear momentum is going to be heavier. Plus, the linear momentum is not just a magnitude, it has a direction. It's a vector. Now, we're going to postulate a first balance law for particles. And that is F is equal to G dot. Okay, so F is the sum of the external forces acting on the particle. G is the linear momentum. G dot is the rate of change of the linear momentum. So F okay. So this postulate, this law, was first proposed in written text for a particle by Newton, and it's called Newton's second law. We cannot prove it. We can observe real life, do a bunch of experiments, and fit this law to these experiments. We can say that this law describes what's happening in the real world under certain conditions. And that's how we come up with it. It's a law that's postulated and that cannot be proven. There's no mathematical proof for this. It just describes reality to some extent. So it's called the Newton's second law. We're also going to call it Euler's first law. So Euler's first law applies for a particle, but also to a rigid body. It extends. Also, the name I'm going to most often use for this is the balance of linear momentum. In a couple weeks or 2-3 weeks, we'll learn about the balance of angular momentum, which is a second law. Not postulated by Newton, but only postulated by Euler. So the balance of linear momentum or balance of linear momentum, I'll abbreviate it like this. So again, it says that if I have a particle, the rate of change of the linear momentum is equal to the sum of external forces acting on the particle. Any questions? 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 If you don't have a question, I have a question. Yes.
G isn't a sum, is it? Or is it?
G is mv. So what is G dot? That's a good question. So if G is equal to mv, what is G dot? It's the derivative of mv, which in general, if the mass of a particle is changing and if its velocity is changing, then that's m dot v plus m v dot. Can you think of a system whose mass could be changing? Yeah, if you have a rocket that's launching, it's losing fuel, its mass is changing. Now, most generally in this class, we will consider systems whose mass is being conserved. So in this case, if the mass of the system is conserved, then G dot is equal to mv dot, which is ma, right? And that's where the F equals ma form of the equation. Good question. Any other questions? I have a question. Under which condition is the linear momentum of a system conserved? Okay. So when is the linear momentum of a system conserved? What does it mean, linear momentum? What does it mean for the linear momentum to be conserved? What is the linear momentum of a system? Of a particle? What is the linear momentum of a particle? Yeah, it's G is equal to mv. So that's conserved, meaning that's constant. So under what conditions is G for a particle constant? The acceleration, that's kind of an equivalent meaning to G if it's constant, because, okay. So the linear momentum of a system is G. So this means that G is equal to a constant. So G is equal to mv is a constant. So the acceleration is 0. But under what condition is the acceleration 0? Yes, exactly. If F is equal to 0. If the sum of all the forces acting on a particle is 0, then its linear momentum is conserved. So again, if the sum of all the forces acting on a particle are 0, then its linear momentum is conserved. So for example, you can think of a particle in space, no weight, no forces acting on it, its linear momentum is going to be conserved. So if it's already moving in a certain direction, with a certain velocity, it's going to keep moving at that velocity forever, unless other forces are being acted on it. Now there are systems whose linear momentum could be conserved in a certain direction, but not totally conserved. It is possible So linear momentum could be conserved in a certain direction only. For example, if I consider a projectile, if I take this piece of chalk and I throw it up in the air, what are the forces acting on it? Yeah, just the weight acting vertically down. So okay. Well, first of all, before we move to the projectile, before we move to the projectile example, I just want to say that when F is equal to 0, that's Newton's which law? If there are no forces acting on the particle, or if their sum is 0, then what's the acceleration of the particle? 0. That's Newton's first law, which you learned about in statics, right? Equilibrium, A is 0. So this is Newton's first law. Statics. We also have Newton's third law. What does Newton's third law say? Yes, exactly. For every action, there's an equal and opposite reaction. Okay. So the F equals ma in the Cartesian basis. Okay. So in the Cartesian basis, Ex, Ey, Ez, I can express the forces as F is equal to Fx, Ex plus Fxy plus Fz. I'll write it down. Questions? Do you have questions? Questions? Okay. So in the Cartesian basis, I can express the force F in terms of the, in the basis. F is equal to Fx, Ex plus Fy, Ey plus Fz, Ez is equal to the mass of the particle, what times the acceleration. Okay. So this F equals ma equation, that's F equals ma, that's a vector equation in 3D space. And from this vector equation, how many scalar equations can I obtain? 3. Exactly. I can obtain 3 scalar differential equations. How? Exactly, by projecting it along 3 independent directions, which I could choose them to be Ex, Ey, Ez, or any 3 independent directions. So I can project along Ex, Ey, Ez, Fx is equal to max, Fy is equal to may, Fz is equal to maz. So before vectors were invented as a mathematical object, that's how the equations of motion used to be written. They used to be written as 3 scalar equations. And they're not any scalar equations, they're 3 scalar differential equations. There are 3 scalar differential equations, which I can solve for the motion. Which can be solved for the motion of the particle, x of t, y of t, z of t, or in other words, for r of t, the position vector of the particle. And if I have x, y, and z, I can calculate the derivatives, x dot, y dot, and z dot. Does that make sense? That if I have x, y, and z in terms of t, I can recreate the motion of the particle. So what the balance law is enabling me to do is to solve for the motion of the particle. That's why we call these 3 equations, or this vector equation, the equation of motion. We're going to talk more about this, though. There's some new ones here. Okay. Shall we take, no, not now. We'll take a 5-minute break in 10 minutes and then we'll reconvene. But for now, let's continue. F equals ma is the balance law, which is equivalent, it's a vector equation in the space, equivalent to 3 scalar equations, differential equations, which we can use to solve for the motion. So technically, it's not as simple because the motion might not need to be described by 3 equations, and this depends on the notion of degrees of freedom and constraints. What is the degree of freedom, or what does it mean? What does degrees of freedom mean? If I have a system, what does degrees of freedom mean? What is it? Yes, that's related. Any other ideas? Right. So the degrees of freedom of a system is the minimum number of coordinates needed to describe the motion of a system. Okay. So the degrees of freedom of a system is the minimum, the degree of freedom of a system is the minimum number of coordinates needed to describe the motion of the system. So if I have a particle in space, so if I have a particle that's moving in 3D space, how many degrees of freedom does it have? How many coordinates do I need to describe the motion of that particle? Show me fingers, everyone. Yes, 3. Now if I have a particle moving in the plane, so I have, for example, a particle that's considered to move in the plane of this table. So how many degrees of freedom does it have? 2. I only need, for example, x and y coordinates to describe its motion. How many constraints is it subject to? It's subject to 1 constraint, right? Which is that it needs to lie on the surface of the particle. So if, for example, if that's z equals to 0, then it's subject to the constraint z equal to 0. So let's write this down. So that's 2 DOF, and how many constraints? 0, here 1. For example, that z is equal to 0. And for example, the two coordinates would be x and y. If I have a particle constrained to move on a straight line, for example, if a particle is constrained to move along this track here, how many degrees of freedom does it have? 1 degree of freedom. How many constraints? 2. If I have two particles in this space, in 3D space, how many degrees of freedom do I need to describe the two particles? 6, right? They're moving independently, so I need 3 coordinates for each. However, if I take these two particles and I connect them by a rod, by a rigid rod, how many degrees of freedom does the system now have? Think. Show me with your fingers. I'm seeing some 4s, I'm seeing some 5s, I'm seeing some 6s. So we have some disagreement. Discuss. How many degrees of freedom do you think it has? How many degrees of freedom does the system have? It's two particles moving in space, but now they're connected by a rigid rod. So they cannot move completely independently. Okay, so what do we think? Show me with your fingers. I see some 5. Everyone's 5? 6? Why is it? Why is it 5? So we originally had 6, right? For each particle, 3. And I added how many constraints using this rod? Just one constraint, that the distance between the two particles is fixed. So that's one scalar constraint. So I'm left with 5 degrees of freedom. Yeah. So if I need 3 coordinates to describe the motion of the position of one particle, and for the other one, I need 2 more. The third one is going to be fixed by this constraint. Yes?
Are we saying that it rotating like around its own axis like doesn't count because like they're particles?
Yes. Okay. Yes. Or else it would be a rigid body, and then for that you would have 6 degrees of freedom. Yes. We'll talk about rigid bodies later. Does that make sense? Questions? So the general idea is that degrees of freedom is the total unconstrained degrees of freedom minus the number of constraints. Scalar constraints gives you the degrees of freedom for the system. Okay, so whenever I have a system, the number of equations of motion that I will need to describe the motion of the system is going to be equal to the number of degrees of freedom of the system. So for each degree of freedom, I'll need a scalar differential equation for that degree of freedom to solve for the motion of the system. So the number of EOMs, so of scalar EOMs needed to describe is equal to the numbers of its degrees of freedom. Is equal to the number DOF degrees of freedom. Okay, so you can imagine if I have a projectile, which is a particle that I just throw, then how many degrees of freedom does this particle have? If I have any particle that I just throw in the air, how many degrees of freedom does it have? 3, right? It's totally unconstrained. How many equations of motion do I need to describe its motion? 3. Okay. So before we solve that problem, let us just write the kind of steps needed to solve a particle kinetics problem. And we're going to be using these steps throughout the semester for solving kinetics problems. Yes?
Sorry, for the example, you said throwing is
Yeah.
the direction that in which you throw, not a constraint.
No, that's considered an initial condition. Yeah. So its constraint is something that would be actively enforced on the particle throughout its motion. For example, if you have a particle moving on a table, then throughout its motion, the particle is touching the table, z is equal to 0. Okay. Okay. Let's take a 5-minute break and then reconvene and start solving problems involving rigid body kinetics. Okay? So until 11:10. Stretch yourselves a little bit. It'll help you focus if you move. Sure.
One is taking MEC 110.
What's that?
It's like a in-person building hardware
It's one of the classes because you need to form a group, but the concept doesn't
online.
Oh.
So we're just thinking of anybody.
Yeah, why not? Ask.
Excuse me, is anybody else in ME 110 for the? No, you? You want to join a group? You already have a group? Oh, okay. Thank you, anyways.
Only one person.
What's
Is
ME
it-
110?
What?
What is ME 110?
It's like project design.
Oh, cool. Good luck.
Do you want to enroll in class?
Oh yeah, I know who that is.
You do?
From the club I go to.
Really?
I believe. I did take a gas mask. I'm just gonna go to my club.
There's only one person. I mean, we should just tell some people that anyone in person.
Yeah. Oh wait, there was a
In person.
Okay. It's 11:10. 1 minute and it will be 11:11. 1, 1, 1. Okay. So projectile motion, consider a projectile, which is a particle that's being thrown in the air with an initial velocity v0, initial position vector r0. Okay, so consider a particle of mass m with initial position vector r at t equals to 0 equals r0, launched with velocity okay, so for the motion of the particle. And gravity is acting vertically down in our system. Okay, so what do I do? I'm following the 4 steps here, right? So I have a particle launched in the air. I have the initial velocity and position vectors of the particle. I need to solve for the motion of the particle. So I'll follow the 4 steps. Number 1, I'm choosing the Cartesian basis because that's the only one I know so far. Okay, so I'm setting up my basis. I can choose the system. What is the system here? Which system am I going to be considering? The particle, right? The particle. So my system is the particle. Later on in the course, or just in a bit, you can consider a system to be, you can consider different systems. For example, if we're going to do a problem where you have a truck that is composed of 2 connected trailers, and you can consider your system to be the first trailer, the second trailer, the bar in between, or like the whole system. So considering your system, choosing your system is wisely is going to be very helpful as you solve problems, and this is going to come with experience. So here it's simple though, our system is just a particle, and I can write the position, velocity, and acceleration of the particle as, in the Cartesian basis, as xex and that would be my step 1. Questions? What is step 2? Draw the free body diagram of the particle. How many forces are acting on the particle? 1, which is just the weight, right? So I'll draw my system. I have 1 force acting on it, the weight, and I can write its expression on the side. The weight is equal to minus, what is the direction of the weight force here? Down, which is along which unit vector? Ez minus mg ez. So that's by step 2. Now once I finish steps 1 and 2, step 3 becomes easy. Step 3 is I want to write the vector equation of the balance law. So step 3, F is equal to ma. F, I go to the free body diagram and I copy all the forces, which is just here minus mg ez. A is what? X double dot Ax, y double dot Ay plus double dot. Questions so far? So step 3 is pretty easy. Once I finish steps 1 and 2, I write F equals ma, the basic expression, and then what is F? I go to the free body diagram, I copy all the forces, and M and A is here. So I'm done. Step 4, I'm going to project and then solve whatever I need to solve for. Okay. So how many equations of motion, scalar equations of motion am I expecting here? How many scalar differential equations of motion am I expecting here? 3, right? For the x, y, and z coordinates. 3. So the first one is going to be for the x coordinate. If I project along Ex, what will I get? If I project this equation along Ex, if I project this side along Ex, what do I get? What is it? 0, right? 0. If I project the other side along Ex, what do I get? Mx double. So that's a pretty simple equation, right? Differential equation. The second one, I'll get the same thing, right? 0 is equal to my double dot. For the third one, what will I get if I project along Ez, this side? Minus mg is equal to mz double dot. So these are my 3 differential equations of motion, scalar differential equations of motion, which I can solve for x. I can say that x of t is equal x dot at t equals to 0, or x dot 0 of x dot 0 times t. Wait, no, so x double dot is equal to 0, so x dot is constant, it's its initial value, and x of t is equal, maybe I'll call that Vx 0, and that becomes Vx0 t plus x0. So that's x as a function of time. How am I getting this? I'm just integrating, but I'm doing it a little bit quickly. Same thing here. Now here, I'll get y double dot, the mass and the mass cancels out. Z double dot z dot of t is equal to minus gt plus vz0 z of t minus g over 2 t squared plus vz0 t plus c0. And I've solved for the motion of the particle. Questions? Yes? Oh, these are just the components of V0 vector. So they're V0 yes. Does that make sense? Okay. Other questions? So my question is now, how would this problem be different if I'm adding a drag force to the problem? I'm going to add a viscous drag force. So not only do I have the weight acting on the problem, but I have a viscous drag. So the drag force. The viscous drag, I'm going to say that it's going to be proportional to the speed of the particle, CV, C viscous drag, or CD drag force, whatever, just a constant. It's a constant times the speed of the particle. So the higher the speed of the particle, the greater the drag force. And I'm going to take the direction of the drag force to be opposite to the speed, the velocity of the particle. So minus V over the magnitude of V. So I have a drag force acting on the particle. It's proportional to its speed, and its direction is opposite to the velocity, which I can rewrite as minus CV. So if I have this drag force acting on the particle, how will my problem be different? What does step 3 become? What do I do? What do I do? Okay, this is my free body diagram, and I added a FT to it. Then what? So steps 1 and 2, 1 is the same. 2, I added the drag force. Step 3, what do I do? What is it? Exactly, the balance of linear momentum. And what do I put here for F in this equation? Yes, I have to put the weight and I have to put the drag force, right? So the weight is minus mg ez. The drag force is minus cv. And ma is the same as before. Okay, so that's 3. Okay. My question is still to solve for the motion of the particle. So what do I do? Yes? I have to project exactly. How many degrees of freedom does this particle have here that is subject to drag? 3, right? So still drag force is not a constraint. It's just an applied force acting on the particle. It's not a constraint. I still have 3 degrees of freedom. I expect 3 scalar equations of motion by projecting along Ex, Ey, Ez, the vector form of the balance of linear momentum. So if I project along Ex, what do I obtain? What is minus mg Ez dot Ex? 0. What is minus Cv dot Ex? So recall V is what? V is up there. So what is minus Cv dot Ex? Mm-hmm. C, not x. So you have to take v, plug it back here. So this v is up there. So when I dot that with ex, what do I get? What is v dot ex? X dot, exactly. I'll get minus cx dot. Minus cx dot is equal to mx double dot. Right? For the second equation, what do I get? Minus cy dot. Raise your hand if you're okay with this, if that makes sense. Okay, so make sure your neighbor understands this so far and get this third equation. Double check that your neighbor understands it, and I'm happy to answer any questions. So set 3 is passing around. Any questions? So what is the third equation going to be? What is the third equation going to be along EZ, projected along EZ? Minus mg minus cz dot is equal to mz double dot. Okay, and now I can solve these equations, and actually I can solve them by hand. So here, minus cx dot is equal to mx double dot. I can solve, well, let us see. Minus c over m x dot. X double dot is dx dot by dt. So I can write this as dx dot over x dot minus c over m times dt, and I can integrate. What's the integral of dx dot over x dot? Ln x, right? Ln absolute value of x dot. I should put x dot 0. Yeah, or the divided or the minus. This is calculus, right? You get x dot as this, and you can integrate one more time, and you can get x as a function of time. Did I make a mistake, or is it? So that you can get x as a function of t, and the same thing for y. Now the z equation is a tiny bit trickier because of the extra term, the minus mg term. So I can do the minus mg minus CZ dot is equal to MZ double dot. What do I do next? Ideas? I'll use the same trick I use here first. I'll do that. That's equal to MdC dot by dt. So what should I do next? This is a separable differential equation. Ideas, ideas, ideas. You can chat with your neighbor if you want. Tell me what they say, because they won't tell me themselves. This is just one step and it becomes separated. What is it? Ideas? Yes. Exactly. So I'll just divide by the I'll keep maybe the minus up, or maybe here. And I can integrate this, but I'll have to use U substitution to calculate this integral. It's still going to be an exponential. Okay? Any questions? So then, in homework 1, raise your hand if you've already looked at homework 1 a little bit. Yes. In homework 1, you're doing the exact same problem. It's a projectile with drag, but the drag force is not viscous drag. It's a bluff body pressure drag. So it's just a prescription for the drag force, where the drag force is not proportional to V. It's proportional to the speed squared. And then in this case, the differential equations you obtain, you cannot integrate by hand anymore. So the homework 1 walks you through integrating them numerically using Python. Or you can use MATLAB or any other program you want. Okay? So homework 1 walks you through integrating differential equations for a different kind of drag numerically. Homework 2 will walk you through just animations. So then later on in the subsequent homework, you'll be like basically solving the differential equations of different systems and visualizing the motion. Does that make sense? I'm okay with you using AI to help you build the visualizations, and that's fine by me. Okay? Don't have AI solve all the homework for you, because then you won't learn anything. And I think it's valuable what you would learn. Okay, any questions? Questions here? So you already have set 3. Let me give you set 4, and let's choose a problem to solve. Just take one if you need one. Okay. So opening up, I have an extra set 4. If anyone needs any set 4s, I have extras. Yeah. Can you so there's one person here at the end. Okay, so these sets are on the website, right? Okay. Set 4. So in this problem set, problem 2 has a solution video online. So solve it yourself. And if you need any help, there's a solution video. And also come to office hours, discussion, add everything. Let's look at problem 3 right now. The woman holding the box in an elevator. So I'm going to erase the board. Okay. So take a couple minutes, chat with your neighbor about this problem, try to solve it, but you need to use the 4 steps. So chat with your neighbor, try to come up with a plan to solve the problem while I erase the board and draw it. Yes, the woman was in the elevator and set 4. Set 4. So again, the woman in the elevator, which is problem 3 of set 4. Problem 3, set 4. Okay, so a 60 kilogram woman holds a 9 kilogram package as she stands within an elevator, which briefly accelerates upward at a rate of g is equal at the rate of g over 4. So the weight g is vertically down, the acceleration of the elevator. So I'm gonna take this, call it EY. So the acceleration of the elevator is g over 4 EY. So a 60 kilogram woman holds a 9 kilogram package as she stands within an elevator, which briefly accelerates upward at a rate of g over 4. Determine the force R which the elevator floor exerts on her feet and the lifting force L which she exerts on the package. So we want to find R and L, force from elevator on woman, and L is the force from woman on package, which exerts on the package during the acceleration interval. If the elevator support cable suddenly and completely fail, what would be the values of R and L? Okay, so again, a 60 kilogram woman holds a 9 kilogram package as she stands within an elevator which briefly accelerates upwards at a rate of g over 4. Determine the force R which the elevator floor exerts on her feet and the lifting force L which she exerts on the package during the acceleration interval. Then we'll do the second part of the question. Okay, so here we want to find R, we want to find L. Which system or systems do I need to consider to find R and L? Let us think. What do you think? Any ideas? Which system or systems should I consider to find R and L? For example, if I consider the whole combined system of the elevator and the woman and the box, will I be able to determine R and L? No, why not? Yeah, these forces become internal to the system. They cancel out because of Newton's third law. So if I want to find, for example, the lift force L that the woman applies on the box, what do I need to consider? Which system do I need to consider? the box alone or the woman alone, right? If I want to consider, if I want to find R, the force that the elevator applies on the woman, which system should I consider? The woman, or the woman and the box. But as long as the woman is detached from the elevator, so that I can kind of find the force in between the two. So if I consider 3 free body diagrams here, if I consider the woman, the box, the woman holding the box. So if I add this system plus this system will give me this system, right? So then what are the forces acting on the box, say? What is it? I have the weight of the box. What else? The force from the woman applied on the box, which we called L. Okay? That's it? Any other forces? I think that's it. Okay, what about the forces acting on the woman alone? The weight of the woman. What else? The normal force or the reaction R from the elevator on the woman. What else? Yes, the force that the box applies on the woman, which is minus L. That's from Newton's third law, right? And if I combine the system of the two, what are the forces acting on the combined system? I have both weights, W of the box, W of the woman, and what else? R. What happens to L? Why don't I have L? Okay. Does this make sense? When I add these two, I get this system. Okay? And I can write on the side. So if I'm following the 4 steps here, I have already put my position vector. So what kind of motion are the box, the woman, and the elevator undergoing? Are they moving in general on the plane and space, or any particular constrained motion? Yeah, they're just going straight up. Actually, it's no degrees of freedom here. All the motion is constrained. The motion of the woman is prescribed by the motion of the elevator. It's the same as the elevator. Okay? So here, for the woman, for the box, R of the woman is Y woman EY. V of the woman is Y dot EY. A of the woman is Y double dot AY. And for the box, same thing. They might be they differ by a constant when it comes to the position vector, but the velocity and the acceleration are the same. R of the box is equal. So these Y dot, Y double dot are equal for the box and the woman. So here, W of the box minus M box G EY, W of the woman minus M woman G EY. The lift to force is L EY, R is I. Okay. Any questions so far? Okay, so if I want to find L, what do I do? Yes, I want to do what? Isolate the box, balance of linear momentum for the box. So for the box, the forces acting on it are L plus the weight of the box is equal to M times the acceleration of the box. L is LEY. And we're given that the acceleration of the box, the acceleration of the woman is equal to what? y double dot is equal to g over 4. Is it going up or going down? Up, so it's g over 4. Okay, so that's m. Okay, so that's, I can project along EY and I can get that L, or I don't even need to project. I can just obtain that L, the force, is equal to m AB, which is g over 4 EY, plus g. Yeah, that's m of the box. I can get L. That's it. I can also get R. Any questions? How do I get R? Yes, I can consider the woman and the box. So okay, so F woman is equal to m of the woman times acceleration of the woman. So that's R plus both, woman and box. Sorry, I'm gonna call it F. Okay, so R plus weight of the woman plus weight of the guy plus weight of the box is equal to m and I can find R. Weight of the woman, which is mb plus mw g plus g over 4 AY. I think that's it, right? And the vector, the force is a vector, and they want a force. I gave them a force, which is a vector. Did I make a mistake? Questions? For the second part of the question, where they ask, what would R and L become if the elevator suddenly starts to free fall? So what do you think we do here? If the elevator is free falling, what is its acceleration? If you cut the cords, yes.
Negative g.
Exactly. If the elevator is free falling, it's like a projectile. If I draw F equals ma for the whole system, it's like a projectile. Okay. The acceleration, if you do F equals ma for the system, you get the acceleration is equal to minus g. So how would R and L change? I would just replace the g over 4 by minus g, and I'll get R and L. So then what would R and L become? 0. So you won't feel any normal force. You're free falling. Everything is just free falling. Okay, no normal force, no reaction force. Everything is going down. Okay? Does that make sense? Questions, questions? So I'm thinking, since we have 15 more minutes, we can do a small quiz from the problem set. You can also do it as a pair work. And let's do from set 3, problem 1. Set 3, problem 1. So you're going to use the ADS is equal to VdV. And here, the acceleration is given in terms of position. So you're given the acceleration in terms of position, and you can integrate to find ADS is equal to VdV. So I'll open Gradescope now. This is going to be due at noon. And you can work in pairs. If you have any questions, I'll pass around. Okay? Okay, and if you're solving in pairs, remember you have to add the names of both of you on Gradescope on the same submission. You can do that. If you don't know how to do that, let me know. I'll show you. Okay. Just 1 second. Enable group submission. What up? Yes, it's rectilinear motions. Particle is moving in a straight line, but the acceleration is given in terms of x. And it's a piecewise function. Wait, I can turn this off, I think. Piecewise meaning that it's not continuous. So you would write, yeah. And here it's an equation of a line, which you can find. So once you find a of x, you can write the piecewise function. You can integrate it. You integrate from -3 to 9, and then the integral you can divide into the 3 intervals, right? And I'm happy to answer questions. Just find the equation of the line. And the triangle works, but
I'm trying the slope and then putting.
yeah. So it passes by the 2 points, -5, -3, and 4, 5. We can find the equation.
I was able to post it. It was in ad.
Awesome, great.
It was just like
Okay.
lying there.
Awesome, great. Yeah, I don't know why I couldn't see.
I think I'll just do it.
Yeah, you have access to it. Okay. Thank you, Megan. Which problem are you doing? No, you should be doing the first one. Not in this set. The rectilinear motion set. Do you really need this in front of you? Can you turn it off? Okay, so the equation of the line, it doesn't pass by x equals to 0, so there should be an intercept, a y-intercept. Yeah, so it passes by -3, -5, -3, and 4, 5.
So we know the acceleration for each of these. Let's be specific.
How's it going?
8 over 9 for -3 to 4.
Questions?
Yeah, just give me a second. I'll see if we can have this.
Yeah, take your time. There should be a y-intercept here because it doesn't pass by the origin.
It's not definite that this is 1, so don't we have to figure out.
Yeah, you just find the equation of the line. It passes by -5, -3, and then 4, 5. You know? Yeah. You can find the slope, then you can find y equals ax plus b and find b. Right, to find the equation of the line that passes by 2 points that you know, you can find the slope. That's one way to do it. Then find y equals ax plus b, find b.
I've known if I'm doing this right.
Well, did you find the equation of the line first?
Yeah, I just did that.
Okay. And then now you need to use this equation. A of x dx. A of x dx is equal to v dv. Can you write it down?
Oh, I guess I kind of wrote that.
And then you integrate, but you split the integral into 3. Integrate, but you can split it into 3. What's the integral of v dv? V squared over 2. Any questions? I won't give you numbers in the exam, so no calculators.
Yeah. But like, I guess for this.
We're going to be in no electronics kind of ones. Okay, so I have the assignment open till 12:15, so make sure you submit by then. And
So I got to the integral of that from -3 to 4. So I just do that.
where? Finding the equation of the line? Yeah. So the line passes by the 2 points, -5, -3, and 4, 5, 4, 5. So the y is equal to x plus b. The slope is 5 minus 3, which is 8, over 4 minus 5, which is 9, right? And then y minus y1 is equal to a x minus x1. You can find that y plus 3. So here it's not y, it's a. And you can find a is equal to 8 over 9x plus 8 over 9 5 plus 3, so you can find the equation of the line. This is the equation of the line, basically. This is basic algebra. Yes.
I'm not really sure what I did wrong. I run you through what I did.
Mm-hmm.
So first for the rectangle, I didn't really have to integrate because you can